So good morning, everybody. Thanks for the invitation and thanks to you for being here. So today, in this masterclass, I will present the first crypto agile hardware accelerator, which is called Phoenix, which is based on an hardware sharing strategy between two post-quantum cryptosystem algorithms, namely ML-KEM and HQC. So just to give a little bit of the introduction, nowadays one of the major problems in the cybersecurity is the quantum threat, meaning that in the future there will be the possibility to have a powerful quantum computer able to completely break the algorithm such as RSA and the one based on the elliptic curve that we use nowadays to protect our data. Fortunately, there is a solution, and the solution is called post-quantum cryptography, which is a new branch of the cryptography, which has the goal of devising a new algorithm based on new hard mathematical problem, where these problems are meant to be secured against classical and quantum attacks. So in the context of the post-quantum cryptography, the NIST recently selected and will standardize the future key encapsulation mechanism algorithm, namely ML-KEM and the HQC. And now the question is how to do what is called the quantum state transition, meaning that we have to pass from using pre-quantum algorithm toward a use case when we will use just post-quantum solution. The idea to accomplish this transition is to use the two approaches. So the first one is called hybridization, where there will be the proposal of application which take into account post-quantum and pre-quantum algorithm. And the next approach is the crypto agility. That is the approach that we will cover in this presentation. So crypto agility means proposing application taking into account different post-quantum cryptography families and so different post-quantum algorithm. The idea behind this approach is that nowadays these post-quantum algorithms are not immature enough to be secured and to guarantee our future security. And so combining different post-quantum algorithms belonging to different families allow us to maintain and to reinforce our future security. In the context of the presentation, we will study the crypto agility between the two NIST standard key encapsulation mechanism, ML-KEM and the HQC. And if we look in the state of the art about this crypto agility regarding the hardware implementation, there are just a few works which implement this crypto agility without using an efficient sharing strategy. So this is actually the problem that we want to cover in this presentation. So, first of all, we are talking about two post-quantum algorithms, ML-KEM and HQC, which belongs on two different cryptographic families, which are the lattice-based and the code-based, and relies on two different hard mathematical problems. However, if you look at the schematics of this mathematical problem, we can see that the security of this problem relies on an introduction of an error, which makes it difficult retrieving the secret data. So at this point, what we can say is that the framework seems closed. However, if we look at the internal parameter of this algorithm, we can notice, for example, with the parameter n, the different size of the polynomial to be processed along this algorithm, and also that the polynomial rings associated to perform the arithmetic operation are totally different. So now the question is how to implement this crypto agility efficiently. Our idea is to try to identify some similar or common operation along this algorithm. And in order to do that, what we can do is to perform, first of all, a software profiling to understand two different things. The first one, which are actually the real operation inside this algorithm. And the second one, which are the operation that will characterize the main bottlenecks. So after performing this profiling, we identified in the hash function and in the polynomial multiplication the two main bottlenecks. So we can try to applying the sharing strategy based on these bottlenecks. What we can say is that applying a sharing strategy of the hash function is straightforward, since because the two operations in order to perform this function along this cryptosystem rely on the same FIPS 202 standards, while performing the sharing strategy on the polynomial multiplication is challenging, because the operation used to perform this operation are different. So our proposal is to introduce an alternative operation, which is called Frobenius additive fast Fourier transform, which we will use to perform the multiplication in the HQC. The introduction of this operation will increase, first of all, the performance of the current bottleneck associated to the two-way Karatsuba operation, and also it allows us to well mutualize with the current number theoretic transform operation, which is used to perform the multiplication in the ML-KEM. So at this point, we identified the sharing strategy to work, and the question is how to implement this sharing strategy in hardware. So we can put ourselves in a system-on-chip scenario, where the system-on-chip is basically the combining different components, different modules inside a single integrated circuits. So this module can be, for example, the microprocessor, which is in charge of executing the instruction, the memory, which keeps the instruction and the data to be processed. Then we will have a system bus, which allows us to exchange the data between the module inside the system on chip. And after, what they can have is some components which are called application-specific accelerators, which are actually the accelerator that we want to implement and that will accelerate the target operations. Talking about this module, we will have two different integration approaches. So we talk about tightly coupled if the accelerator is directly integrated in the microprocessor, and we talk about loosely coupled if the accelerator is attached on the system bus. And this point is not only a question of finding the sharing strategy, but to understand how this sharing strategy can be efficiently implemented in hardware. So in this case, we will talk about hardware resource sharing, where the scenario that we want to meet is the proposal of a unique sharing hardware accelerator, which is not only able to improve the performance of the target operation, but also to take less resources in terms of hardware with respect of the sum of the standard-alone accelerator for the target algorithm. So now we will describe a little bit the two polynomial multiplication techniques. So first of all, in general, how to perform the polynomial multiplication using FFT. So the main idea is to perform this operation in three different steps. So the first one, in the first step, which is called FFT, we will take as input two polynomial, and we will evaluate based on a new basis, in a new polynomial basis. Then we will compute the result. We will perform the multiplication using the pointwise multiplication step. And after, in order to get to the final result, we evaluate it back using the inverse FFT steps in order to retrieve the result in the correct polynomial basis. What that is interesting to see is that in the FFT and in the EFFT steps, this operation follows a regular structure, and this operation relies of the utilization of what that we call the processing element. So if we put the case of the number theoretic transform, we always rely on a polynomial multiplication FFT based, where this polynomial multiplication is performed on a finite field. And if we look at this processing element inside the FFT and the EFFT steps, we can see that they have a shape of a butterfly structure. So if we enter into the details about this butterfly, what that we can find are operations such as modular addition, modular subtraction, and modular integer multiplication, which are performed on finite field. Talking about the pointwise multiplication in the entity is complex because each evaluated point are represented using two coefficients, and so one of the possible optimization that we can use to perform this operation are the utilization of the two-way Karatsuba, which another time can be executed using butterfly structure. So looking the state of the art about the hardware implementation of the entity, what that we can find are configurable hardware implementation, which take into account all the butterfly that we have seen so far for this operation, and which relies of the same polynomial rings in order to perform the arithmetic operation. Now we will look at the alternative operation which is called Frobenius additive fast Fourier transform. So the idea is the same. We will have a polynomial multiplication FFT based, where in this case in the FFT and in the EFFT steps we have another time butterfly structure. If we look into the details inside this butterfly structure, we have a totally different arithmetics operation, which in this case relies on the carryless addition and on the modular carryless multiplication. So what that I wanted to highlight is that these operations are totally different with the one that we can see in the entity. What did we do as the first contribution about this work is, first of all, to implement this Frobenius technique starting from an existing implementation in the state of the art. Then, to identify the operation to be accelerated in hardware, we performed a profile of the different steps contained in this operation. And as expected, we identified the FFT and the EFFT as the main bottlenecks. Then, once implementing this operation, we integrate it in the HQC for all the NIST security level. And comparing our result with the baseline reference implementation relying on the two-way Karatsuba, we show us a performance speed up between 3.7 and 8. Now we will go a little bit of the detail of the real context of this presentation by explaining our hardware resource sharing strategy. So our idea is to propose a configurable hardware design which is called the Super Butterfly, which is able to replicate and to perform all the different butterfly structure seen along the target polynomial multiplication operation. The Super Butterfly integrates two entity butterfly and one Frobenius additive butterfly, and also integrate some arithmetics operation which takes into account the different mathematical foundation of this technique. So we proposed two hardware elements, so the Agile modular arithmetics and the Agile modular multiplier. So the first one allows us to manage the carryless addition and the modular operation. Our idea is to perform the modular operation as using just addition, exploiting the two-way complementary representation. And if we look how it is possible to solve a given modular operation, we can say that we can have two possible results. So the first result, which will not use the modular reduction itself, and the second result, on which we have to integrate the module constant in order to bring back the result in the correct finite field. So we implemented these two different scenarios using the hardware and using specifically the first and the second branch of our hardware design. And in order to manage the carryless addition, we will use the carry save adder placed on the second branch of the component. Then we also implement an agile modular multiplier, where a given modular multiplication is performed using two different steps. So the first step is to compute the scalar multiplication, and the second step is to apply the reduction. So for our agility, we focused on the first step, and we proposed an approach which is based on a carryless two-way Karatsuba operation. So the two-way Karatsuba takes as input two polynomial, two data, and split them into parts. And at the end, in order to compute the final result, we have to compute three temporary values, which are called Z0, Z1, and Z2, which can be computed using multipliers. So these multipliers, in our case, are carryless multiplier based on a schoolbook-based architecture. And the execution of the entire operation allows us to perform the carryless multiplication. However, if we introduce the possibility in the multiplier 1 and the multiplier 0 to propagate inside the carry, we can also manage integer multiplication, which is our case when performing this operation for the entity butterflies. Then we implement this super butterfly structure, and we integrate in a more complex loosely coupled accelerator that is called Phoenix, which not only allow us to verify all the possible configuration that we estimate to be performed using super butterfly, but also allow us to accelerate the entire FFT and the EFFT operations. Furthermore, we introduce an optimization for the ML-KEM, because actually in this algorithm the operation to be performed are not just one single polynomial multiplication, but are multiplication represented as vectors polynomials. And so we also succeeded to implement this operation fully in hardware. Talking about the result, which are the most interesting part. So we integrate our solution in a system on chip using the ZIPO Z7 board. So we implement Phoenix, use the available RTX Z7, and we run the entire system on chip at a working frequency of 125 MHz. And we integrate Phoenix for all the NIST security level of ML-KEM and HQC. In order to evaluate the impact of Phoenix in terms of resources, we compare just using the NTT hardware state-of-the-art, because nowadays there is not work about the Frobenius integrated in the HQC. And what that we demonstrate is that our solution is aligned with the current state-of-the-art if we want to perform the NTT in cycles. And taking into account the number of hardware resources, we have an impact between 1.2 and 3.2 in terms of the resources. This is nowadays the current impact for the introduction of the agility in hardware. Then we will discuss the performance of this cryptosystem after the integration of Phoenix. So first of all, we take into account the integration in the ML-KEM, we evaluate our result in terms of speed up factor because of the different platform on which nowadays is possible to find entity integrations. So we compared our result with the first reference, and what that we can notice is that in terms of result is pretty aligned, although the first references integrate the entity using tightly coupled approach. Then we compared our solution with the second reference, and what that we can see is that the second reference performed have a better result due to the fact that they also integrate some assembly optimization of the FIPS 202 function, which, as we have seen during the first part of the presentation, as the main bottleneck of the ML-KEM. So the history is different for the HQC. What that we can do is to compare our result, so the impact of Phoenix, which the first contribution, because as I said before, there is no state of the art about the integration of the Frobenius in the HQC. And what that we can notice is that the introduction of Phoenix improved the performance in terms of speed up factor between 2 and 2.4. After we introduced a further optimization for the HQC, which relies of keeping some data in the FFT domain, and so although doubling the size of the public key, what that we can have is a further speed up of 1.15 for the encapsulation and the decapsulation function. At this point, we arrived to the conclusion. So what we understood in this presentation is that the crypto agility is the key for maintaining the future security of our post-quantum solution. We demonstrate in this presentation that the introduction of an alternative polynomial multiplication operation allows us not only to improve the performance of one of the cryptosystems, but also to propose a sharing strategy in terms of the polynomial multiplication between two cryptosystems relies of the two different cryptographic families. So, as an ongoing improvement in SOA, what that we want to prove is that our solution in terms of resources consumed less resources with respect of the sum between the entity and a given Frobenius additive accelerator, and we also working of better valorize the performance of Phoenix in the ML-KEM algorithm using a different platform based on the RISC-V approach. So thank you for your attention. If you have some questions, some information, curiosity, we have in the stand D29, if I remember well, and we can discuss and take a coffee together.
Thank you so much. You can applaud Antonio. Starting on fire, but it's normal when you're
Just
Phoenix.
in time, c'est parfait.